Good morning and welcome to this next lecture on vibrations of plates and shells. So, we are in the topic of the Rayleigh-Ritz method, and I am following this book by Elanco and Monterrubio. So, the last part I would like to present is about admissible functions, okay, how to choose admissible functions. The book has some interesting things to say, so I am just going to present it. You can try this out. So, now one thing is that the straight polynomials are not good when it comes to large matrices. Okay. And the book states that even transcendental functions have problems in terms of implementing restraints. Okay. Now, lower order polynomials are fine in numerics, and higher order transcendental functions are fine with numerics. Okay. So, the strategy is this: strategy is to find admissible functions that are good in terms of numerics for an unrestrained system. Okay. And then use penalty functions. That is the strategy. Okay. So, in this regard, the authors present a set of functions that are complete. That means they are capable of representing every boundary condition. They are linearly independent. Okay. And they have derivatives at least till half the order of the PDE. Okay. That means in the energy term, all derivatives must exist. Okay. And they present this set of functions. Okay. They say phi 1 of x is equal to 1, phi 2 of x is equal to x by L, phi 3 of x is x by L whole squared, and from the higher values or higher order terms onwards they implement the transcendental cosine terms, okay, I starting from 4, 5 and so on. Okay. Together they satisfy all boundary conditions, all possible boundary conditions. Okay. For an unrestrained system. Okay. So, how does the displacement function look like? It looks like A1 plus A2x by L plus A3x by L whole squared and some I from 4th to some n, let us say AI cos I minus 3 pi x by L. Okay. So, the example is that of a free beam, that is the unrestrained 1D system. Okay. So, you have a free beam, and if you want to implement restraints, rotational restraints, then use a rotational spring with a penalty. If you want to restrain vertical displacements, use a vertical spring with penalty. If you want to implement restraints rotationally, okay. And they show very good convergence and very good numerical behavior for a large number of terms. The tables are presented in the text, not showing them here. And last is, if you want to implement your potential energy term, it's EI by 2 integral x equal to 0 to L del 2 W by del x square squared dx, that is the original beam potential energy. Then you include your spring energy at x equal to 0, the spring energy at x equal to L. Then you can have rotational del W by del x squared at x equal to 0. You can have rotational spring maybe 1 and 2 del W by del x whole squared at x equal to L, and the kinetic energy function rho a by 2 integral 0 to L W square dx plus m0 by 2 W square at x equal to 0 plus m1 by 2 W square at x equal to L, then I0 by 2 del W del x squared at x equal to 0 plus I1 by 2 del W by del x whole squared at x1 equal to x equal to L. Okay. Now I close the topic from the textbook. Okay. Now we will move on to two dimensional systems, okay, Rayleigh rates for plates and shells. Okay, we want plates and shells. These topics are also covered in the textbook, but I'm giving a different perspective now, a different material, okay, because it's good to know all angles. So now the general strain energy, the general strain energy term for a general shell, okay, the du is now sigma 11 epsilon 11 plus sigma 22 epsilon 22 plus sigma 12 epsilon 12 dV, and sigma 11 is equal to E over 1 minus mu squared epsilon 11 plus mu epsilon 22 sigma 22 is equal to E by 1 minus mu squared epsilon 22 plus mu epsilon 11, and so half sigma 11 epsilon 11 is equal to half E by 1 minus mu squared epsilon 11 plus mu epsilon 22 into epsilon 11, which is 1 half E by 1 minus mu squared epsilon 11 squared plus mu epsilon 11 epsilon 22. Similarly, half sigma 22 epsilon 22 is 1 half E by 1 minus mu squared epsilon 22 squared plus mu epsilon 11 epsilon 22. And so the du is rewritten as E by 1 minus mu squared epsilon 11 squared by 2 plus epsilon 22 squared by 2 plus mu epsilon 11 epsilon 22 plus g by 2 epsilon 12 squared and dV. Okay. So now if the ui's are implemented as some capital Ui e to the power of I omega t, and we take the max value, that is e to the power I omega t is 1, then my V max, okay, is given by integral alpha 1 alpha 2 alpha 3 E by 2 1 minus mu squared epsilon 1 squared plus epsilon 2 squared plus 2 mu epsilon 1 epsilon 2 plus g by 2 epsilon 12 squared and a1 a2 d alpha 1 d alpha 2 d alpha 3. Now epsilon 1 1 is given by 1 over A1 del alpha 1 U1 plus alpha 3 beta 1 plus U2 plus alpha 3 beta 2 by A1 A2 del A1 by del alpha 2 plus U3 by R1. Okay. Epsilon 2 2 is 1 over A2 del alpha 2 U2 plus alpha 3 beta 2 plus U1 plus alpha 3 beta 1 by A1 A2 del A2 by del alpha 1 plus U3 by R2. And epsilon 1 2 is equal to A2 by A1 del alpha 1 U2 plus alpha 3 beta 2 by A2 plus A1 by A2 del alpha 2 U1 plus alpha 3 beta 1 by A1, where beta 1 is equal to U1 by R1 minus 1 by A1 del U3 by del alpha 1, and beta 2 is U2 by R2 minus 1 by A2 del U3 by del alpha 2. And the kinetic energy term, okay, the kinetic energy term is 1/2 rho integral alpha 1 integral alpha 2 integral alpha 3 U1 dot plus alpha 3 beta 1 dot whole squared plus U2 dot plus alpha 3 beta 2 dot whole squared plus U3 dot squared A1 A2 d alpha 1 d alpha 2 d alpha 3 further is equal to rho by 2 integral alpha 1 integral alpha 2 integral alpha 3 U1 dot squared plus 2 alpha 3 beta 1 dot plus alpha 3 square beta 1 dot squared plus U2 dot squared plus 2 alpha 3 beta 2 dot plus alpha 3 beta 2 dot squared plus U3 dot squared A1 A2 d alpha 1 d alpha 2 d alpha 3. Now if we integrate alpha 3 square with respect to alpha 3 from minus h by 2 to h by 2, then we will get alpha cube over a small thickness h, which is h cube. So we are going to neglect that term. Okay. Okay, we are going to neglect this term alpha 3 squared, yes, going to ignore those terms. And if alpha 3 is integrated from minus h by 2 to h by 2, you get alpha 3 square by 2 over minus h by 2 to h by 2, and that goes to 0 because the square term. So, this also goes, this also goes. So, we are left with this which has nothing to, no coefficient alpha 3. So, the integral gives an h. So, we get rho h by 2 integral over alpha 1 integral over alpha 2 u1 dot square plus u2 dot square plus u3 dot squared a1 a2 d alpha 1 d alpha 2. So, within the Kirchhoff level approximation or Euler-Bernoulli level approximation, our omega square, the Rayleigh quotient, looks like this: 1/2 integral alpha 1 alpha 2 alpha 3 e by 1 minus mu squared epsilon 1 1 squared plus epsilon 2 2 squared plus twice mu epsilon 1 1 epsilon 2 2 plus g epsilon 1 2 squared a1 a2 d alpha 1 d alpha 2 d alpha 3. Okay, this is Vm. Okay, and the psi m is rho h by 2 integral alpha 1 integral alpha 2 u1 square plus u2 square plus u3 square a1 a2 d alpha 1 d alpha 2. Okay. So, this is for the a general plate or thin shell. Okay. You can implement Rayleigh on this now. Okay. So, now as a continuance to this topic of Rayleigh method, I will present one very useful paper. It came out in Journal of Sound and Vibration 1985. The details are this from pages 493 to 499. The title is Natural Frequencies of rectangular plates. Rectangular plates using characteristic orthogonal polynomials in Rayleigh method. Okay. The author is RB Bhat. Okay. So, now if we implement this term for a rectangular plate, okay. So, there A1 is equal to 1, A2 is equal to 1, R1 is equal to infinity, R2 2 is equal to infinity. And epsilon 1 which is x is equal to del u x by del x plus z del beta 1 by del x. And what that means is I am taking alpha 1 as x and alpha 2 as y and alpha 3 is z. And if you take pure bending, then ux is 0. Okay, pure bending, the mid plane does not stretch, ux is 0 on the mid plane. So my epsilon xx becomes minus z del 2 w del x square. Okay. Similarly, epsilon y becomes minus z del 2 w by del y square, and epsilon xy becomes minus 2z del 2 w by del x del y. Okay. So how does this term look like for a rectangular plate? The numerator looks like half integral over x, integral over y, integral over z, e over 1 minus mu squared, z squared del 2 w by del x squared whole squared plus z squared del 2 w by del y squared whole squared plus twice mu z squared del 2 w del x squared del 2 w del y squared. Okay, plus g into 4 into z squared del 2 w by del x del y squared dx dy dz. Okay, that is the numerator. Okay, you work with it further. 1/2 integral x y z e by 1 minus mu squared z square outside. Let me use the notation wxx squared plus wyy squared plus twice mu wxx wyy plus 4 gz squared wxy squared dx dy dz. So this gives me half integral x integral y e h cube by 12 1 minus mu squared wxx squared plus wyy squared plus twice mu wxx wyy plus e by 1 plus mu, okay, h cube by 6 wxy squared dx dy. Okay. So now this ends up as 1/2 integral x integral y e h cube by 12 into 1 minus mu squared w xx squared plus w y squared plus twice mu w xx w y plus twice into 1 minus mu w xy squared dx dy. Okay. So that's the numerator. Okay. The denominator is rho h by 2 integral x integral y u1 square plus u2 square plus u3 squared dx dy. Okay. The time is up, so I will close the lecture here and continue. Thank you.